Okay, so at the previous lecture we introduced Banach algebras, and we proved that the spectrum of any element of a unital Banach algebra is compact and non-empty. And today our first goal will be to discuss the spectral radius in Banach algebras. So suppose that A is a unital Banach algebra, and little a is an element in the algebra. And we define the spectral radius of A as follows. R of A, this is the supremum of the absolute values of points in the spectrum. So we know that the spectrum is non-empty, so this is well defined. And also we know that the spectrum is compact, and so this number is finite. So geometrically, this is the radius of the smallest closed disk centered at 0 and containing the spectrum. So we can draw the following picture. So if this is 0, and for example, this is the spectrum, then this is the disk whose radius is the spectral radius of A. So we already know something about this number. Namely, we already know that the spectral radius is less than or equal to the norm of A. And essentially, this was proved at the previous lecture. If I'm not mistaken, this was Theorem 2. Essentially, we proved that for each lambda in the spectrum, the modulus of lambda is less than or equal to the norm. And so when we take the supremum, we see that the spectral radius is less than or equal to the norm. In some cases, this is an equality. Here are some examples. Example 1. Suppose that A is the algebra little than infinity of x, the algebra of bounded functions on any set x. Then for each element of this algebra, the spectral radius equals the norm. Well, indeed, we know that the spectrum of A is the closure of A of x. This was one of our first examples of explicit calculation of the spectrum. So the spectrum of A, little a is a function, is a bounded function on x. And we know that the spectrum of A is the closure of A of x. But on the other hand, the norm is the supremum norm. This is the supremum of elements in A of x. And so this implies that this equality. And essentially the same, not essentially, exactly the same result holds for the algebra of continuous bounded functions on any topological space. The same holds for the algebra CB of x, for the algebra of continuous bounded functions on any topological space. Another example of the same kind, example 2. Suppose now that A is the algebra of linear operators on a finite dimensional Hilbert space. A finite dimensional Hilbert space. So H is isomorphic to Cn for some n. And suppose that little a is an element of our algebra, that is, an operator on a finite dimensional Hilbert space, such that the matrix of this operator is diagonal in some orthonormal basis of H. Then the spectral radius. What is the spectral radius? First of all, the spectrum of A, the spectrum of a matrix, is just of a diagonal matrix is consists of numbers on the diagonal. So the spectral radius is the maximum of these numbers. And on the other hand, we know that the norm of such an operator, the norm of a diagonal operator, equals the maximum of these numbers. So again, in this case, we see that the spectral radius equals the norm. And here's a counterexample. Let A be the algebra of operators on the two-dimensional space. That is essentially the algebra of 2x2 matrices. And let little a has the following form. Well, the spectrum of an upper triangle matrix, again, consists of numbers on the diagonal. So we see that the spectrum is 0. So the spectral radius is also 0. But of course, the norm of this operator is positive, because the operator is not 0. So this example shows that this inequality is strict in general. In fact, this example can easily be generalized as follows. This is a useful exercise. If A is any unital algebra, and little a is a nilpotent element, is a nilpotent element of A, then the spectrum of A is 0. The spectrum of a nilpotent element is 0. So this explains why the spectrum of this matrix is 0. It is nilpotent. Okay, now we have the following general result, which gives a useful formula for the spectral radius. This is the so-called Berlin-Gilfond formula. If A is a unital Banach algebra, and little a is an element in the algebra, then the spectral radius of A equals the following limit and also it equals the following infimum of the same sequence. Well, actually, this general formula is due to Gilfond, and Bern, some time before Gilfond, proved this in a very special case for some concrete Banach algebra of weighted convergent power series. But the general case is due to Gilfond. To prove this formula, first of all, we observe that it suffices to show that, first of all, the spectral radius is less than or equal to the infimum, to this infimum. This is the first inequality. And the second inequality, the spectral radius is greater than or equal to the upper limit of this sequence. If we prove these inequalities, then we are done, because so in general we know that in the theorem of any sequence of non-negative real numbers is less than or equal to the lower limit. This holds for each sequence of non-negative numbers. And the lower limit is less than or equal to the upper limit, again for each sequence of real numbers. So these inequalities hold always, and if we prove 1 and 2, then we get the following chain. And this chain shows that actually all inequalities in this chain are equalities. So in particular, our way equals this infimum, and since the lower limit equals the upper limit, we conclude that the limit exists, the sequence converges, and the limit equals our way. So we have to prove inequality 1 and inequality 2. Inequality 1 is very easy. Well, indeed, if you take any point in the spectrum of A, then we have the following inclusion. Lambda to the power n belongs to the spectrum of A to the power n. This follows from the polynomial spectral mapping theorem. Follows from the polynomial spectral mapping theorem. And this implies that the absolute value of lambda to the power n is less than or equal to the norm of this element. And if we now take the nth root, we get the following. And finally, we take the infimum over n, and we get inequality 1. Okay. Let's now prove inequality 2. This is slightly more involved and more interesting. To prove inequality 2, we consider the following disk. We let D denote the open disk on the complex plane of radius 1 over our way. If the spectral radius is 0, then D is just the complex plane. So we'll let 1 over 0 equal infinity. But if R is if the spectral radius is positive, then this is a disk. Next, we take any bounded linear function on our algebra. And we consider the following function. Let's denote this function by psi f. This is a function defined on the disk, on our disk. And this function is given by the following formula. So what can we say about this function? First of all, let's see that this function is indeed defined everywhere on D. Because if you take any non-zero number lambda in the disk, then we can write this function in the following way. This is minus lambda inverse. And here we apply f to A minus lambda inverse, and then take the inverse. And this is defined, this is well defined because, well, lambda is in our disk. So lambda satisfies this inequality, and this implies that lambda inverse is outside the spectrum. Lambda inverse is bigger than RA. So this is outside the spectrum, and so this element is invertible. This element is invertible. And of course, psi f clearly is defined at 0. So this formula implies that psi f is defined everywhere on the disk. Also, we know that, so what is this? This is the resolvent function applied to lambda inverse. This is the resolvent function applied to lambda inverse. And we know that the resolvent function is holomorphic everywhere. So this implies that our function psi f is holomorphic everywhere in the punctured disk. Psi f is holomorphic on the punctured disk on D minus 0. And finally, if we look at our initial definition of f, of psi f, we conclude that this function is continuous at 0 because the inversion operation is continuous. This is one of the properties of the multiplicative group in the Banach algebra. So this function is continuous at 0. In particular, it is bounded in the neighborhood of 0. And now it's a classical fact from complex analysis that if you have a function which is holomorphic on the punctured disk and which is bounded in the neighborhood of 0, then this function is holomorphic everywhere. This function is holomorphic everywhere on the disk. Okay, so what do you know about functions holomorphic on a disk? Well, we know that such functions can be decomposed in Taylor series. So psi f of lambda can be written in the following form. This is the Taylor series of our function. Let's now calculate the Taylor coefficients, Cn. To calculate the Taylor coefficients, we consider a smaller disk. So this is our initial disk of radius 1 over RA. And we now consider a smaller disk of radius 1 over the normal way. Since the spectral radius is less than or equal to the norm, then this number is less than or equal to this number. So in the smaller disk, we have the following formula for each lambda such that lambda is smaller than 1 over the normal way. We have the following. First of all, this implies that the norm of lambda A is strictly smaller than 1. And so we have the following expression. Essentially, this is the geometric progression. This formula was proved at the previous lecture. This was Theorem 1 from the previous lecture. Okay, and if we now apply the functional f to both sides of this equality, we get that psi f of lambda equals the following sum. F of an lambda to the power n. So if we look at the little disk, we see that in the little disk we have this decomposition and this decomposition. But the Taylor series is unique. And by the uniqueness of the Taylor series, we conclude that Cn equals f applied to a to the power n for each n. Okay, so let's now come back to this decomposition. And we remember that this decomposition holds everywhere on the big disk. So this series converges everywhere on the big disk. And in particular, this sequence is bounded. The sequence Cn lambda n is bounded for each lambda in D. Okay, but now we know what Cn is. Cn is f applied to a to the power n. So this is nothing but f applied to lambda n a n. This is bounded. And now let's recall that f, what was f? F was an arbitrary bounded linear functional on A. So this holds. This holds for each bounded linear functional on A. For each bounded linear functional on A, this sequence is bounded. And now let's recall a corollary from the Barnstein theorem. We know that if we have a set in a normal space such that all bounded functionals on this set take this set to a bounded set, then the set itself is bounded. So the Barnstein theorem implies that the sequence lambda n a n is bounded. There is a positive constant C such that the norm of this element is less than or equal to C for all n. Okay, so this can be written as follows, the following equivalent form. So the absolute value of lambda is less than or equal to c to the power 1 over n divided by the following. So we just we divide by the norm of a to the power n and then take the nth root of both sides. Well, this holds for each n, so we can now take the upper limit and conclude that the modulus of lambda is less than or equal to the upper limit of what? C to the power 1 over n goes to 1. Whatever C is, this goes to 1. So this is less than or equal to the upper limit of maybe let me write it in a slightly different way. 1 over the no, that's better. Oh, I see. This is not the best way of writing this inequality. I choose something. I choose a different way of rewriting this inequality. So the norm of a to the power m, and then to the power 1 over n, is less than or equal to c to the power 1 over n divided by the modulus of lambda. This is equivalent. This is equivalent, but this is more convenient for us. And now we take the upper limit. Now we take the upper limit. So what what do we see? C to the power 1 over n goes to 1. So this is less than or equal to 1 over the modulus of lambda. And now we recall that this inequality holds for each lambda in the disk. Well, here we assume that lambda is non-zero. Now this inequality holds for each non-zero number lambda in the disk. And so when lambda goes to the radius of the disk, that is to 1 over R of A, we get the following inequality. And this is exactly what we wanted to prove. Okay, so this completes the proof. Let's now look at some corollaries of this formula. Corollary 1. The spectrum of our element little a is 0, even only if the spectral radius is 0. This means that the following limit is 0. And more explicitly, this means the following. This means that the norm of a to the power n is has the following property. In other words, this means that the norms of the norm of a to the power n goes to 0 very quickly. So it goes to 0 faster than any geometric progression. Well, why is it so? We just write the definition of the limit. So for each positive epsilon, there is a number n such that this number is smaller than epsilon for big numbers n. And when we take the nth power, we get that I to the power n is less than epsilon to the power n. And since epsilon was arbitrary, we can write the little o here. So for example, this holds if the norm of a to the power n behaves something like 1 over n factorial. This goes to 0 faster than epsilon to the power n for each positive epsilon. There is a special name for such elements. Such elements are called quasi-nilpotent. Such an element A is called quasi-nilpotent. If it is nilpotent, then of course this condition is satisfied because this sequence is eventually 0. But it can happen that this sequence goes to 0 very fast, but is not 0. And here is a classical example of a quasi-nilpotent element, which is not necessarily nilpotent. This is the Volterra operator, which you probably remember from one of our first lectures. An example and exercise at the same time. So let's look at the Volterra operator. This operator acts on let b equal to space on a closed interval. And it is given by the following formula. Vf of x equals the following integral. I claim that this operator is quasi-nilpotent. And actually we have two exercises here. The easy part is to show that this operator is quasi-nilpotent if big K is bounded for each bounded measurable function K. And the difficult part 2, this is the difficult part, is to show that this operator is quasi-nilpotent for each square integrable function K on the square. So this is more difficult. In case 1, some elementary analytic estimates show that the norms of this operator go to zeros, behaves like something like 1 over n factorial. So everything follows from this formula. And here's another useful corollary of the Gilfond formula, corollary 2. Suppose that A is a unital Banach algebra and suppose that B is a closed subalgebra of A, closed subalgebra, such that the identity of A belongs to B. So they have a common identity element. Then, for each element little b in the smaller algebra, we have the following inequality. The spectral radius doesn't depend on the choice of the subalgebra. If you take take any smaller closed subalgebra, then the spectral radius remains. The spectral radius doesn't change. And let me recall that in general, if you take smaller subalgebra, the spectrum with respect to B can be strictly bigger than the spectrum with respect to A. So the spectra are different, but the spectral radius is the same. And it is the same for the simple reason that it is given by this formula. This is the spectral radius. It is defined in terms of the norm of A. And so it doesn't depend on the choice of the subalgebra. Okay, so now we leave the general theory of Banach algebras and we concentrate on the algebra of bounded linear operators on a Banach space. So we are going to discuss spectra of bounded linear operators. And in particular, we will see that the spectrum of a bounded operator it can be naturally divided into several disjoint parts. So we'll also discuss parts of the spectrum. So let X be Banach space. Over the complex numbers. So when we deal with the spectrum, we always work over the complex numbers. And let T be a bounded linear operator on X. So by the spectrum of T, we always mean the spectrum of T considered as an element of B of X, of the algebra of all bounded operators on X. Before we define parts of the spectrum, let's look at some non-invertibility reasons for our operator. There are several non-invertibility reasons. First of all, if T is not invertible, it can happen that the kernel of T is non-trivial. This is the first possibility. On the other hand, it can happen that the kernel of T is trivial. By the way, in the finite dimensional case, this is the only possibility, because in the finite dimensional case, we know that the kernel is trivial, if and only if the operator is invertible. But in the infinite dimensional case, it can also happen that the kernel, as I said, non-trivial, non-trivial. So T is not invertible. If the kernel is non-trivial, then the operator is not invertible. And it can also happen that the kernel is trivial, but the image is not. The image is strictly smaller than x. That is, T is not surjective. Now we remember the open mapping, the inverse mapping theorem, which tells us that there are no other possibilities. So if T is not, in other words, if the kernel of T is trivial and the image of T equals x, then T is bijective. And we know that a bijective linear operator on a Banach space is a topological isomorphism. So it is an invertible element of this algebra. For technical reasons, it is convenient to divide this second case into two subcases. So subcase 1 is the case where the kernel is trivial, the image is smaller than x, but the image is dense in x. The image is dense in x. And the second subcase is the case where the kernel is trivial, but the image is not dense in x. And now, by looking at this picture, we can introduce the following three parts of the spectrum. We'll have the following definition. We define the point spectrum of T as follows. This is sigma P of T. This is the set of all lambda for which the kernel of T minus lambda is non-trivial. In other words, this is the set of all eigenvalues of T. The point spectrum is the set of all eigenvalues of T. In Russian, this is точечный спектр. Точечный спектр. The second part is called the continuous spectrum. The continuous spectrum, in Russian, непрерывный спектр. The continuous spectrum, sigma C of T, consists of those points lambda which are not in the point spectrum, so they are not eigenvalues, with the property that the image of T minus lambda is different from x, but is dense in x. This is the continuous spectrum. And finally, we define the residual spectrum. Of T. And this is the set sigma R of T, which consists of those points lambda, which are not in the point spectrum, and such that the image of T minus lambda is not dense in X. not dense in X. And the rational residual spectrum is остаточный spectrum. So according to this picture, we see that the spectrum of T is the disjoint union. The spectrum of T is the disjoint union of the point spectrum, the continuous spectrum, and the residual spectrum. By the way, a warning. Some authors of some papers and textbooks define continuous spectrum, sometimes define continuous spectrum in a slightly different way. So be careful when you read a paper or a book. Look what the author means by the continuous spectrum. For example, if you take the well-known book by Reed and Simon, Methods on Modern Mathematical Physics, then they adopt slightly different definition of the continuous spectrum. And if you take their definition, the union is not disjoint. But we take this definition. Of course, in the finite dimensional case, we have only one part of the spectrum. And spectrum equals the point spectrum, and the continuous spectrum and the residual spectrum are empty. Let's now look at the infinite dimensional situation. And here is our simplest example. It's proposition 1. Let's look at the parts of the spectrum of the diagonal operator. So let X be the little LP space, where P is greater than or equal to 1, but is finite. Or we can take also the little C0 space of sequences which vanish at infinity. We choose a bounded sequence alpha. So this is an element of little L infinity, a bounded sequence. And we consider the diagonal operator, M alpha. This is an operator on X, which is given by the following formula. So this operator just multiplies by alpha. I claim that the spectrum of this operator is the closure of all the elements in our sequence. The point spectrum is exactly the set of all elements in our sequence. The continuous spectrum consists of all elements in the spectrum which are not in the point spectrum. And so the residual spectrum is empty. Okay, so let's now try to prove this result. For each n, let's denote by En the following sequence. So with identity at the nth slot and 0 elsewhere. And clearly we have the following inequality. M alpha applied to En is alpha n En. In other words, En is an eigenvector for our operator, and alpha n is the respective eigenvalue. So this formula obviously implies that all elements in our sequence are in the point spectrum. Well, also it's rather easy to see that there are no other points in the point spectrum. For convenience, let's observe that for each lambda, the operator m alpha minus lambda is also a diagonal operator. Namely, this is the diagonal operator m beta, where beta n is alpha m minus lambda. And if lambda is not in our sequence, then all the beta n's are non-zero. And since they are non-zero, it's easily seen that the kernel of this operator is trivial. The kernel of this operator is trivial. And since this is just m alpha minus lambda, we conclude that lambda is not in the point spectrum. And hence one concludes that the point spectrum is precisely the set of all elements in our sequence. This is the point spectrum. Well, the point spectrum is contained in the spectrum. But we know that the spectrum is compact. And in particular, the spectrum is a closed subset of the complex plane. So this inclusion implies that the closure of the set of all elements in our sequence is contained in the spectrum. Now we want to show that this is inequality. The spectrum is exactly the closure of this set. To prove this, we consider the following map. Consider a map phi from little L infinity, from the algebra of bounded sequences, to the algebra of bounded operators on X. And phi takes each bounded sequence alpha to the respective diagonal operator m alpha. And let's observe that phi is a unital algebra homomorphism. Phi is a unital algebra homomorphism. So what can we say now about the spectrum of m alpha? This is the spectrum of phi of alpha. But we know that a unital algebra homomorphism doesn't decrease the spectrum. So this is always contained in the spectrum of alpha. This is a very simple algebraic property of the spectrum. But what is this? Well, we know that the spectrum of a bounded sequence, more generally the spectrum of a bounded function, alpha is the closure of its image. So this is the closure of the set of all elements alpha n. And if we now compare this and this, we conclude that the spectrum is exactly the closure of this set. Okay, so we now know that the spectrum is the closure of the set. The point spectrum is exactly the set of all elements in the sequence. So the final step is to show that all elements in the spectrum which are not eigenvalues are in the continuous spectrum. Indeed, if lambda is not in the point spectrum, that is, lambda is not an element of our sequence, then again beta n, this is beta n, all elements beta n are non-zero. And this easily implies that each vector En, this is our En, sits in the image of m beta because it has the following form. So it sits in the image of m beta. On the other hand, the linear span of all these elements En is dense in X. So X is little p where p is finite, or little c0. In all these cases, the linear span of all these elements En is dense, and so we conclude that the image of M beta is dense in X. So lambda is not in the residual spectrum, so the residual spectrum is empty.
Why now dense when it's enclosure?
What is not dense?
If lambda is not.
If beta n is not 0. Okay, so this formula holds. So this element is in the image of M beta. Okay, so the linear span of all these elements is dense. All of them are in the image, so the image is also dense. Mm-hmm. Well, we know that our operator acts from LP to itself. It acts from X to X. So the image is contained in X, because we consider M alpha as an operator from X to itself. The image, of course, is contained in X. But the point here is that it is dense in X, because actually we don't have to worry about infinite linear combinations. We know that finite linear combinations of these vectors are dense in X. And all of them are in the image. And so the image is bigger than the linear span. The image of M beta is bigger than the linear span of all these elements En. It can be, it can happen that it is, the image is already X. It can happen that the image is smaller than X. But in all cases, the image will be dense in X, because it contains all elements En. Of course, it's essential here that P is finite. Otherwise, this argument fails. Okay, this completes the proof. So this shows that the points, the residual spectrum is empty, and so the continuous spectrum consists of all points in the spectrum which are not in the point spectrum. This result can be generalized to arbitrary multiplication operators. This is proposition 2. Suppose that we have a sigma finite measure space, omega mu. Sigma finite measure space. And let X be the big LP space, LP of omega mu, where P is finite. We take an essentially bounded measurable function f. This is an element of the big L infinity space. And consider the respective multiplication operator. The multiplication operator, MF, is the operator on X, given by the following simple formula. So this is just the pointwise multiplication of f and g. I claim that the spectrum of this operator is the set of all essential values of f. So we discussed this notion a couple of lectures ago. So a complex number is an essential value of f if the measure of the preimage of any neighborhood of this point is positive. So the spectrum of this operator is the set of all essential values of f. The point spectrum of this operator consists of those elements, of those numbers lambda, such that the measure of the respective fiber of the preimage of lambda is positive. The continuous spectrum is the spectrum minus the point spectrum. It is the set of those essential values for which this measure is 0. And finally, the residual spectrum is empty. So in the special case where omega is a set of natural numbers equipped with the counting measure, we see that proposition 2 reduces to proposition 1. So proposition 1 is a special case of proposition 2. The proof is a useful exercise for you. So some parts of the proof of proposition 1 have analogs in proposition 2. But some parts don't have such analogs. So this is a bit harder than proposition 1. By the way, another useful exercise. What happens if p equals infinity? Both in proposition 2 and in proposition 1 and then proposition 2. Okay, the next property of the spectrum is almost trivial, but nevertheless it is very useful, so let's write it down. This is proposition 3. Suppose we have two operators, say S and T. S is a bounded operator on the Banach space X, and T is a bounded operator on the Banach space Y. And so we suppose that they are similar. Suppose they are similar. So let's recall what it means. This means that there is a topological isomorphism. Topological isomorphism between X and Y, which makes this diagram commute. Then I claim that they have the same spectrum, the same point spectrum, their continuous spectra are the same, and their residual spectra are also the same. This is also an exercise, almost trivial, because essentially it's enough to observe that if S and T are similar, then S minus lambda and T minus lambda are also similar. And if two operators are similar, and one of them is invertible, or has a trivial kernel, or has a dense image, then all these properties are all the same properties hold for the second operator. Okay, as an application of this trivial result, let's calculate the spectrum of the bilateral shift operator. This is proposition 4. So we look at the operator TB. This is the operator on the little space over the integers. And this operator acts by the following formula. Well, this operator is called the bilateral shift. In Russian, двусторонний сдвиг. Of course, essentially this is, in fact, this is the right shift operator, but it is called the bilateral shift for the reason that the sequences are indexed by, not by natural numbers, but by integers. I claim that the spectrum of this operator is precisely the continuous spectrum. So in this case, we say that the spectrum is purely continuous. And this is the circle bold T. So this is the circle, the unit circle on the complex plane, centered at 0. And so, as a corollary, the point spectrum and the residual spectrum are empty. So there are several ways of proving this result, but perhaps the easiest approach is to apply proposition 3. So for each integer n, we let fn be the function on the circle T given by the following formula. And we know that the family of all such functions, fn, is an orthonormal basis in the big alpha space on the circle. This is essentially the trigonometric system. So this is an orthonormal basis. And now from the general theory of Hilbert spaces, we see that there is a unitary isomorphism. Unitary isomorphism U between the big L2 space on the circle and the little L2 space over the integers, which takes each fn to En, where En is the same En as in the previous proposition. Okay, so we have the bilateral shift on the little L2 space and an isomorphism, a unitary isomorphism between the big L2 and the little L2. So let's look at the corresponding operator on the big L2 space. So let S be U inverse TB U. This is the operator on the big L2 space. And this operator is similar to the bilateral shift. So to complete the proof, it's now enough to calculate the spectrum and the parts of the spectrum of S. But what is S? Well, T is the right shift, essentially. So TB satisfies the following formula. It takes En to En plus 1 for each n. And by the definition of S and by the definition of U, we conclude that S takes each Fn to Fn plus 1 for each n. But what is Fn plus 1? So this is the formula for Fn. Fn of z is z to the power n. So Fn plus 1 is F1 multiplied by Fn, the pointwise product. And since the linear span of all the functions Fn is dense in the big L2 space, this is an orthonormal basis, so the linear span is dense, we conclude that S is nothing but the multiplication operator, the multiplication by F1. And F1 is just the identity map of the circle. Take Z to itself. And now the result, the rest of the proof, follows from the previous proposition. More exactly, from propositions 2 and 3. So this is the multiplication operator, and we already know everything about the multiplication operator. So the spectrum is the set of all essential values of f. But here's a little exercise. If we have a function on the circle which is continuous, obviously F1 is continuous, then the essential values are precisely the values. So this is just F1 of t, which is t itself. This is obviously empty, because F1 is the identity map of the circle onto itself. And the preimage of each point is a point. And the measure of a point is 0. So this is empty, and hence the continuous spectrum is the spectrum. So the spectrum is purely continuous. Okay. So this is the spectrum of the bilateral shift. Now the last series of tricks for calculating spectra is based on the duality theory. I have the following result, which is proposition 5. Suppose that X is a Banach space, and T is a bounded linear operator on X. I claim that the spectrum of T equals the spectrum of the dual operator T star. The proof is very easy for the following reason. What do we know about T and T star? We know that T is invertible if and only if T star is invertible. This was one of our results from the duality theory. An operator between Banach spaces is a topological isomorphism, if and only if the dual operator is a topological isomorphism. So lambda, a complex number lambda, is not in the spectrum of T, if and only if T minus lambda is topological isomorphism. And this happens if and only if the dual operator is a topological isomorphism. But the dual operator of T minus lambda is T star minus lambda. And so this operator is a topological isomorphism if and only if it is an invertible element in the algebra of bounded operators. That is if and only if lambda is not in the spectrum of the dual operator T star. And that's it. So T and T star have the same spectrum. Okay, now how about the parts of the spectrum, T and T star? Well, to answer this question, let's recall the following fact from duality theory. If T is a bounded operator on the Banach space, then property 1, the image of T is dense in X if and only if the kernel of T star is trivial. Property 2, if the image of T star is dense, then the kernel of T is trivial. And property 3, if our space X is reflexive, then the converse is also true. If X is reflexive, then the image of T star is dense, if and only if the kernel of T is trivial. So we already proved these results some time ago. Now let's apply them to the calculation of spectra. So we have the following proposition, proposition 6, which is almost immediate from these results. So again, X is a bounded space, and T is a bounded operator on X. Then we have the following relations. Relation 1. The point spectrum of T is contained in the union of the point spectrum of T star and the residual spectrum of T star. And just let's see why that's so. Well, indeed, if lambda is in here, then we know that lambda is in the spectrum of T star. But lambda cannot be in the continuous spectrum of T star because we'll here and replace T by T minus lambda. If lambda is in the continuous spectrum of T star, then the kernel of T minus lambda is 0, and lambda cannot be in the point spectrum. This is a contradiction. So if lambda isn't here, it cannot be in the continuous spectrum of T star. So it is either in the point spectrum or in the residual spectrum. Okay, on conclusion 2, the continuous spectrum of T is contained in the union of the continuous spectrum of T star and the residual spectrum of T star. Again, why is it so? If lambda is here in the continuous spectrum of T, if we suppose that it is in the point spectrum of T star, then T star minus lambda has non-trivial kernel. We'll here and conclude that the image of T minus lambda is not dense in X. This is impossible because lambda was in the continuous spectrum. So lambda is not in the point spectrum, and it is either in the continuous or in the residual spectrum. In conclusion 3, the residual spectrum of T is contained in the point spectrum of T star. And this is again immediate from part 1. If lambda is in the residual spectrum, then the image of T minus lambda is not dense, and so the kernel of T star minus lambda is non-trivial. So lambda is in the point spectrum of T star. Now let's try to interchange T and T star here. Of course, we must be careful because X can be non-reflexive. But nevertheless, of course, we cannot do it formally, but nevertheless, we have similar inclusions. Namely, the point spectrum of T star is contained in the union of the point spectrum of T and the residual spectrum of T. And in fact, this is immediate from 2. If lambda is in here, it cannot be in the continuous spectrum because of this inclusion. And so it must be either in the point spectrum or in the residual spectrum. Inclusion 5, the continuous spectrum of T star is contained in the continuous spectrum of T. So this is not a direct analog of 2 in the continuous, of course, thank you, in the continuous spectrum of T. So this is even stronger than part 2. So in this case, we can say more. And this is immediate from 1 and 3. Because if lambda is here, it cannot be in the point spectrum of T because of this inclusion. And it cannot be in the residual spectrum because of this inclusion. So it must be in the continuous spectrum of T. And finally, the residual spectrum of T star is contained in the union of the point spectrum of T star and the continuous spectrum of T star. Oh, sorry, of T, of course, of T. Unfortunately, we cannot just forget about this set. It's essential that here we have the union of 2 parts. And well, why is it so? This follows from this inclusion. If lambda is here, it cannot be in the continuous spectrum of T because of this. Oh, it can be in the continuous spectrum. And it's okay. But it cannot be in the residual spectrum because of this inclusion. Okay, so it cannot be in the residual spectrum of T because of this inclusion. And so it is either here or here. In the case where X is reflexive, these inclusions can be a little bit simplified, if X is reflexive, then conclusion 7. So if X is reflexive, we can interchange T and T star here, because T and T double star are similar. And if we interchange T and T star here, we see that the continuous spectra of our operators are the same. And also, this conclusion can be simplified. We can take conclusion 3 and interchange here T and T star. And we see that the residual spectrum of T star is contained in the point spectrum of T. Okay, so all these results are emitted from these general effects from the duality theory. Let's now look how it works in concrete situations. So as an application, and this is our final result for today, let's calculate the spectrum and the parts of the spectrum of the left and right shift operators on the little p spaces. Proposition 7. So let X be the little p space. For simplicity, we assume that p is strictly bigger than 1 and is finite. And let TL and TR denote respectively the left shift operator and the right shift operator. The left shift and the right shift operators. Let's introduce some notation. Let's denote by bold D the open unit disk on the complex plane, centered at 0. We denote by D bar the closed unit disk on the complex plane. This is the closure of D. And as before, we denote by T, bold T, the unit circle. I claim that, so the first part is about the left shift. The spectrum of the left shift operator is the closed disk. The point spectrum of the left shift is the open disk. The continuous spectrum of the left shift is the circle. And so the residual spectrum is empty. This is the full information about the left shift operator, about the spectra, or the part of the spectrum of the left shift operator. As for the right shift operator, we have the following. The spectrum of the right shift operator is again the closed disk. The point spectrum of the right shift operator is empty. The continuous spectrum of the right shift operator is the circle. And the residual spectrum of the right shift operator is the open disk. So in some sense, almost all points in the spectrum of the right shift operator are in the residual spectrum. Well, the shortest way of proving this result is to use these duality inclusions. So first of all, we observe that the norm of each of the operators equals 1. The norm of the left shift operator and the norm of the right shift operator is 1. And since the spectrum, since the spectral radius is less than or equal to the norm, we conclude that the spectra of our operators are contained in the closed disk. The spectrum of the left shift operator is contained in the closed disk, and the spectrum of the right shift operator is contained in the closed disk. The next step is to calculate explicitly the point spectrum of the left shift. In some sense, this is the first step, the initial first step. So when you want to calculate the spectrum, the easiest part usually is to calculate the point spectrum, because this is the set of all eigenvalues. Let's look at the following equation. TL of x equals lambda x. So what is this? So the left shift operator shifts to the left. So this is equivalent to the following system of equations. Xn equals lambda xn plus 1 for each n. And this means that x has the following form. We have x1, x2 is lambda x1, x3 is lambda x2, or lambda squared x1, and so on. Excuse me? What is wrong? Oh, thank you. Of course. So this is lambda x. You're right. This is lambda x, and this is TL of x. So lambda xn equals xn plus 1. Thank you. So now x2 equals lambda x1. x3 equals lambda x2. Okay, so now I hope it's okay. So this is lambda x, and this is TL of x. Okay. We have LP, but this doesn't matter, because if x1 is non-zero, then it's clear that this element belongs to LP, if and only if lambda, the modulus of lambda is less than 1. So if x1 is non-zero, then we see that this element x sits in LP, if and only if the modulus of lambda is smaller than 1. So this implies that the point spectrum of the left shift operator is the open disk. The point spectrum is the open disk. Okay, but we know that the spectrum is contained in the closed disk. And now we see that it contains the open disk. And since the spectrum is closed, we can conclude that the spectrum of the left shift is the closed disk. So we proved this and this. Now let's calculate the point spectrum of the right shift operator. So this is lambda x, and the R of x has the following form. So this means that exactly that lambda x1 is 0, and lambda xn equals xn minus 1 if n is greater than or equal to 2. I claim that this element, this can happen only if x is 0. So if x is non-zero, then there is no such lambda. Well, indeed, if lambda is 0, then clearly the kernel of TR is 0, and so x is 0. And if lambda is not 0, then the first formula implies that x1 is 0. Now we look here and conclude that lambda x2 is 0, so x2 is 0. And then by induction, we see that all the coordinates are 0. So this implies that the point spectrum of the right shift operator is empty. And we have this. Now to deal with the remaining parts of the spectrum, we use the duality theory. So maybe I have to choose where to write. Is it okay if I continue here? Because I want to keep the statement, and I also want to keep this proposition 6. So now we define Q. So Q is a number between 1 and infinity such that 1 over p plus 1 over q equals 1. So this identity uniquely determines Q. So we know that there is a canonical isomorphism between LQ and the dual of LP, and the other way around, because we assume that P is strictly bigger than 1. This is essential. And we know that this isomorphism implies that the dual of the left shift operator is similar to the right shift operator on LQ, and the dual of the right shift operator on LP is similar to the left shift operator on LQ. For convenience, let's denote our operators as follows. So the operators, the left shift operator and the right shift operators on LP will be denoted by TLP and TLQ respectively. TLP and TRP respectively. So the reason is that we will need to consider such operators not only on the LP space but also on the LQ space. So to distinguish between them, we introduce this superscript. Okay. So now let's look at the spectrum of the right shift operator on LP. So since the dual of this operator is similar to the left shift operator on LQ, we have the following inequality. But we already know that the spectrum of the left shift is the open, the spectrum of the left shift operator is the closed disk. This is a closed disk. So we have this quality. Okay, now let's use the already proved result that the point spectrum of the left shift operator is the open disk. So the point spectrum of the left shift operator on LQ is the open disk. Okay, we now use this inclusion. So this is contained in the union of the point spectrum of the right shift operator. Oh, well, maybe it's better to take LQ here. This is not essential, but let's take the operator on LQ. So by part 1 here, this is contained in the union of the point spectrum of the right shift on LP and the residual spectrum of the right shift on LP. Okay, but we know that the point spectrum of the right shift operator is empty. So this is the residual spectrum of the right shift operator on LP. And the residual spectrum of the right shift operator on LP is contained in the point spectrum of the left shift operator on LQ. This is part 3 of our proposition. This is contained in the point spectrum of the left shift on LQ. By the point spectrum of the left shift on LQ is the open disk. So this is the open disk. This is the same open disk. So this implies that all the inclusions in this chain are equalities. And so the residual spectrum of the right shift on LP is the open disk. And we have this. Now, well, the parts of the spectrum are disjoint. The spectrum is the closed disk. And this implies that the continuous spectrum of the right shift is the circle. And we have this. Now, well, our space is reflexive because P is bigger than 1 and it's less than infinity. We can now apply this equality. We apply this equality and we conclude that the continuous spectrum of the left shift operator, on LP equals the continuous spectrum of the right shift operator on LQ. And this is the circle. So we have this. And again, since the parts of the spectrum are disjoint, and the spectrum of the left shift is the closed disk, we conclude that the residual spectrum of the left shift is empty. And this completes the proof. Okay, so this is a nice illustration of this duality trick. By the way, it's interesting and instructive to try to prove this result, I mean proposition 7, without using duality. This is possible, but this is not so easy. Okay, oh, sorry, let's go to the fun. Okay, so that's all for today. At the next lecture, which will be our last lecture in this course, we give a survey of compact operators. This will be essentially a survey. I will not prove most of the results because we have only one lecture. But nevertheless, as far as I know, many of you are not going to attend the course on operator theory, which will be in next term. And well, I think that you have to know at least something about compact operators. So I'll give a brief survey of compact operators on the next lecture. And a more detailed exposition of this theory will be given in the next course on operator theory. Thank you.